All right, welcome everyone. This is New England Dynamics and Number Theory seminar, and we have Sam Chow from Warwick, who will tell us about dispersion and Littlewood's conjecture.
Thanks, Dimitri. So thanks for the opportunity to speak. It's a pleasure to do so. This is joint work with Niclas Technau. So I'll mention again when we get to the theorems. This is some work in diophantine approximation. It's conjecture is a famous problem in diophantine approximation, and also strong links to dynamical systems, and also relates to distribution modulo 1. That's what dispersion is about. So let me start with something that's known in the business as the corollary to Dirichlet's theorem. This is if you want to approximate a real number by rationals, then you can do it with this sort of quadratic approximation rate. So infinitely often is what the IO stands for. We have the rational numbers A over n. If distance to alpha is at most 1 over the denominator squared. This is okay. So and let me also for ease of notation, because there will be more stuff going on later. Let me say we can rewrite this and multiply both sides by n squared, and then we get absolute value of n alpha minus a times n. So a will have to be the closest integer to n alpha if we want this to be a good approximation. So we can rewrite this as n times the distance from n alpha to the nearest integer is at most 1. Okay, and here you can already see this is about the distribution of n alpha modulo 1. Now this is quite an easy result to prove. It's, I guess, the first notable application of the pigeonhole principle. And in spite of the simplicity of the statement and of the proof, it's still basically sharp. So you can put a root 5 the denominator. There's Hurwitz's theorem, but you can't do any better. There are numbers where you can't beat this by an arbitrary constant, and these are called badly approximable numbers. They include the golden ratio. So let's have a look at some badly approximable numbers. So yeah, what this is saying is that you can't beat that by an arbitrary constant. So n times the distance from n alpha to the nearest integer stays away from 0. So it's at least some constant depending on alpha. It's 1. And there's a nice characterization of these. So this is saying that the continued fractions coefficients are bounded. Right? So there's some bound on all of the continued fraction coefficients, and I'll show you remind you what this looks like on the next slide. This continued fraction expansion. This is a nice characterization which essentially enables us to realize the set of badly approximable numbers as a limit or a union of nice fractals. On the topic of fractals, the set of badly approximable numbers does have full Hausdorff dimension. So the Hausdorff dimension is 1, the same as the real line, and I'll also tell you or remind you about Hausdorff dimension. This will also play a role in this work. But 0 Lebesgue measure, so at least almost every number is not badly approximable. For a random number, you can beat Dirichlet by an arbitrary constant. And the typical examples about quadratic irrationals. So these are where you get eventually periodic continued fraction partial quotients. There are of course many more badly approximable numbers, but these are sort of very typical examples, and it's a big open question of whether higher degree algebraic numbers are badly approximable. Most people believe that they're not. Okay. So now let me show you let me show you continued fractions. So we have this continued fraction expansion, and this is this infinite expression, but what does that mean? It means when we truncate it, we get some rational numbers, and their limit is the number we started with, alpha. Okay, so we start with an integer, a0, this is the floor, and then all the successive coefficients, the partial quotients, they're positive integers. And these are the best approximations. There's no closer approximation. There's no rational that's closer to alpha with a smaller denominator. They're the best approximations in an even stronger sense than that. And in particular, they're explicit examples, explicit realizations of the corollary to Dirichlet's approximation theorem. So if you like, this is an explicit way to find the denominators n such that n times the distance from n alpha to the nearest integer is less than 1. This is what was claimed in Dirichlet. So there's a continued fraction algorithm. There are recursive formulas for the numerators and denominators, pk over qk, of these convergence. And I haven't written them down explicitly, but you can see a glimpse of them here. So if you use those, you can calculate that if you have a badly approximable number alpha, then you can look at the ratio of successive denominators and apply the recursive formula. And because the AKs are uniformly bounded, what we find is that this ratio is at least 1 plus c for some positive c. So it forms a lacunary sequence. Lacunarity of the sequence, it will play a role in this talk. However, I'll say that we don't really need alpha to be badly approximable. If we had some other number, then we could just take every second denominator and we would still get lacunarity of that subsequence. And if we took a number that wasn't necessarily badly approximable, but had some sort of diophantine condition, which meant it wasn't rational or extremely well approximable, then everything else I say would still work. However, it's nice to note that the denominators of the continued fraction convergence themselves form a lacunary sequence in this case. Alpha is badly approximable. Okay. So as I said, I'd tell you about Hausdorff dimension. So we can define the Hausdorff S measure for any S, say positive and less than or equal to 1 of some Borel subset of the reals. And this is a generalization of the Lebesgue measure. If you take S equals 1, then you get Lebesgue measure. And what it's saying is we want to cover we want to countably cover the set in the most efficient way possible. And we're not just taking boxes of the same size. We can take potentially sets some that are smaller and some that are larger, and we're trying to optimize this function here, sum of diameters to the s. And this s, I guess you can think of as yes, what happens to the measure when you scale. And so for Lebesgue measure, say s would be 1, and so in this way you can measure sets with sort of non-integer fractional dimensions, non-integer dimensions there. And the Hausdorff S measure sort of goes from infinity in the beginning and drops down immediately to 0, and anything can happen at the critical value of S, and the critical value is called the Hausdorff dimension. And this is a measure of size, and it's a refinement, I guess, can be considered as a refinement of the Lebesgue theory. For instance, if you have a set of Hausdorff dimension less than 1, not full Hausdorff dimension, then certainly has Lebesgue measure 0. And Hausdorff dimension can be used to study sets with Lebesgue measure 0, such as the badly approximable numbers, which have full Hausdorff dimension of 1. In some sense, they're not too small. So, so this is, I mentioned Littlewood's conjecture in the title, and this is, this is a major open problem in diophantine approximation, so in number theory, and it's also a major open problem in dynamical systems. There's something called the Dani correspondence, which takes it to a problem in dynamical systems in spaces of lattices, and it can be interpreted as a special case of the rigidity conjecture of Margolis. And this Dani correspondence, this viewpoint, dynamical viewpoint, was used by Einsiedler and Katok and Lindenstrauss to show that it's true for not only for almost all alpha and beta, which was already known by Gallagher in the 60s, but also for all alpha and beta away from a set of Hausdorff dimension 0. So if there are any exceptions, they form a set of Hausdorff dimension 0, a very small set. And there have been also been other great results towards Littlewood's conjecture. Very few explicit results, so I do want to say a little bit about that. So there are some very easy cases where, say, one alpha and beta are linearly dependent, then sort of approximating one approximates the other, or if alpha is not badly approximable, then we could already beat Littlewood by an arbitrary constant beat Dirichlet by an arbitrary constant without using beta. So that case is also sort of trivial. So we can assume that alpha and beta are badly approximable when we're trying to solve Littlewood's conjecture. Otherwise it's trivial just by using one of them. And so sort of prototype for trying to solve Littlewood's conjecture would be to look at root 2 and root 3, sort of nice examples of badly approximate numbers, and the problem is still open there. So there is a nice explicit result. So this is by Castles and Swinnerton and Dyer, who showed that Littlewood is true with an extra root log if you have two numbers that lie in the same cubic field. And Peck strengthened this to show that Littlewood's conjecture is actually true with a full logarithm to spare in this case where you have two numbers that lie in the same cubic field. So as for the truth, well, so not everyone believes that Littlewood's conjecture is true. There's some grounds for skepticism, but I think sort of the majority view that it's true, and maybe even that it's true with an extra log. So if cubic irrational is the worst case, then there's this extra log, and there's also a volume heuristic. So you can rewrite this as break it into these hyperbolic regions. Right, if we reintroduce the numerators a and b, and then you work out the total area of these hyperbolic regions, and you get something infinite. Right, so I guess these symbols are sort of absorbing multiplicative constants. And another reason is so there's a paper by Badziahan where he shows the sort of the result in the opposite direction, where Littlewood can't be true by more than a log times a log. So if this is sort of homing in on the truth, if the truth is that it's true with an extra log, and the author of that paper, Dmitry Badziahan, also should be able to get rid of log, but nobody's been able to do it. Okay, so I want to talk about some results that are metric, but they're also well thought. So I sort of alluded to the fact that Gallagher had proved Littlewood almost surely, and Einstein the cutoff in Lindenstrass in fact proved it away from a set of Hausdorff dimension 0. But if you look at results that hold Lebesgue almost surely, say this doesn't say anything about badly approximable numbers. So you can assume that the two numbers are badly approximable. The set of badly approximable numbers has Lebesgue measure 0. So Lebesgue measure is not a suitable way to study that. There have been some results in terms of Hausdorff dimension. So Haynes, Jensen, and Christensen said if you take any badly approximable number, alpha, then for full dimensional set of badly approximable beta, you can get Littlewood to be true with a root log extra. And also there's a new uniformity to this result. So it's an inhomogeneous result, which generalization, which means that you can look at distance from n beta minus delta to the nearest integer, which is interpreted as approximation by shifted fractions, or looking at the distribution of n beta at around an arbitrary point delta modulo 1. And there's a uniformity in the sense that delta isn't fixed here. So the set G of allowed beta does not depend on delta. This full measure set where this works for all delta. And the reason that this works is because of discrepancy theory, which I'll get to soon, which sort of tells you about the entire distribution modulo 1. So this was slightly strengthened by Technau and Zafiropoulos, and I also worked with Zafiropoulos on the subsequent paper to generalize this so we could make it doubly inhomogeneous and also sort of widen the set of allowed alpha to allow to get a result with a generic diophantine condition that includes badly approximable numbers. But the results of all of that was only a slight quantitative strengthening. And what I want to talk about today, we do have a lot of results, and it is a lot more general, but I want to talk about this strengthening of the right-hand side. So the quantitative strength of the result. And so it goes from beating Littlewood by a root log to beating Littlewood by about a log. And so the reason why this might be significant is because Littlewood maybe is only true with the log. So maybe this is about the right this is the right sort of strength to look for. And as we'll see, the main difference is that we use dispersion theory, and discrepancy theory sort of can't really hope to do much better than what Haynes, Jensen, and Christensen got. There's with dispersion theory, you do get you do win the full logarithm. So let me now describe the general strategy. So the way you get full dimension. So we want to do some sort of measure theory, and the way you get full. Well, firstly, how you get the measure theory to work and how you get the Hausdorff dimension rests on using these measures that Kaufmann constructed. It's a sort of symbolic dynamical construction. So Kaufmann constructed measures on badly approximable numbers with polynomial Fourier decay. This enables you to sort of count the number of approximations up to a certain height pretty well, almost surely using a sort of L2 sort of concentration argument by counting in Fourier space. And we'll see something like this later on. But as well as saying that you get sort of full measure with respect to some measure, we also want to say something about the Hausdorff dimension, and this is gotten at via the Frossman dimension, or the Frossman exponent of the measure. This can be taken arbitrarily close to 1. And this sort of measures the, as I said, what happens when you dilate, what happens to balls, and what happens to the measure of balls. So it's a somewhat natural notion of dimension, that you can you can relate this to the measure of the set, so measure of the support, say, by the mass distribution principle. So it's a result that works in the converse direction to Frossman's lemma. It says that if you support if you support a measure, if you support a measure with Frossman dimension at least S, then the Hausdorff dimension of the set is at least S.
Okay, Sam, can I ask? So is it supported on by any chance on the set of Bentley approximable numbers with uniformly bounded coefficients, or?
Right. So I didn't say it was fully supported on BAD. So the way I'm thinking about it is, yeah, if you give me some S that's, say, pretty close to 1, then I'll truncate the coefficients by some number like 1 million, according to what S
basically
is.
build a Cantor set with
Sorry?
So you build basically a Cantor set with finitely many branches.
That's right. So if you truncate the continued fraction partial quotients, if you bound them all by m, then you get something like a Cantor set. It's attractive and iterated function system, is I think the way it's now understood. So Kaufman's construction was generalized by Keflek and Ramire, and then by Jordan and Southston, who showed basically that you can do it with more general digit sets as well, as long as the Hausdorff dimension is bigger than a half. But yeah, that's right. So it's because when you cut off the digits at some m, say, you get a very nice you get a very nice structure. Yeah, you can just set. Yep. So that may play a role in some future work, but here we just use this the fact that you get some measure supported on BAD. Okay, but there's two properties. So the polynomial Fourier decay enables us to get sort of results for sort of metric results where we look at generic approximation rates for this measure with respect to this measure, and this Frossman dimension says that then if you have positive measure, then you get dimension at least S, and therefore dimension 1. So Haynes, Jensen, and Christensen, they use discrepancy. So discrepancy theory is very classical topic. So there's use for numerical integration, but it's also just very nice theoretically. So it relates very nicely to exponential sums by Weil's equidistribution theorem and Weil's criterion and the Erdős-Turan inequality. So what this is you take a ball, you take some interval, and you look at the number of points in this interval. So you've got points mod 1 or points between 0 and 1. You look at the number of points in this interval, or the proportion of points in this interval, and you subtract the probability or the statistical proportion, expected proportion, which is the length of the interval. And you take the biggest difference between those. And there's this notion of uniform distribution mod 1 or equidistribution if this discrepancy goes to 0, as n goes to infinity. And you can quantify this, so you can get effective can get an effective decay rate here often. And if you have a uniform random variable, so random heuristics will also play a role. If you have a uniform random variable, there's a lot of the iterated logarithm for the normalized discrepancy, n times discrepancy at n. So the point of this really is that the discrepancy is about n to the minus half if you have IID uniform random variables. So if we're working on a concrete problem, we can't hope to do better than what we get for uniform random variables, unless something very special is happening. Yeah, in the settings we will consider, we're sort of aiming for randomness and expecting random statistics. So now let me talk about the strategy. So if you take this convergence, you get good approximations to alpha. And then if you run along this sequence of convergence, we then want to approximate beta, or approximate beta inhomogeneously, so, and with some effective rate. And if we can show that the discrepancy decays, then there will be some, if we choose capital T large and we choose little t at most capital T, there'll be something where this is small. So if the discrepancy is very small, then in any small box, we'll be able to find something. So in the small box around delta mod 1, we'll be able to find some nt times beta. So bounding the discrepancy will tell us that for any delta, we can find some nt beta close by mod 1. And so this is what they do, Hans Jensen and Christensen. So they sort of use this principle that if you take some Lachenary dilate of a random number, so random, either Lebesgue random or random with respect to some Fourier decaying measure, then you should get something. You should get something random, and it should behave like uniform random. And they're able to demonstrate this. So there's also a lot of the iterated logarithm known in this context, but in particular, they're able to show that the discrepancy is bounded. So random would be t to the minus a half, and they can get t to the epsilon minus a half. And this can be strengthened a little bit, but not well, not beyond what you would get for random sequence. And that gives this Littlewood with an extra root log. Yeah. So that's what they did, and so we also take the same overall strategy, where we look at we do some Lachenary approximation. So we say, look at the convergence or some Lachenary sequence of good approximations to alpha. And then we try to approximate beta by looking at the distribution of nt beta on this sequence. So we prove this Lachenary approximation result. We have it with respect to any polynomially decaying measure. And we get that we can approximate beta inhomogeneously and uniformly in the shift with this approximation rate. Now this looks like 1 over t, which is sort of the random dispersion coming in, and then times this log cubed, which is I guess the loss, technical loss. But in particular, yeah, we get this, which is stronger than what you would get from discrepancy theory, and this might look quite abstract. So we can apply it with Lebesgue measure, and we can also apply it with Kaufman measure. And Lebesgue measure, there are also other techniques. So I guess it's more interesting to apply this with Kaufman measures, and then we also get results for badly approximable numbers in that way, which relates to Littlewood's conjecture. So we can assume that the numbers are badly approximable. So this is this is a step on the way to major step on the way to getting the multiplicative result. And this also is something sort of abstract, like there's a notion of Fourier dimension. And this says that the exceptional set has Fourier dimension 0, meaning it doesn't support a decaying measure. There's also some sort of notion of size. It's less than relative to the Hausdorff dimension, although it's possible for the Hausdorff dimension to still be 1, and the Fourier dimension is 0. So this is not enough to say that to get any decay in the Hausdorff dimension of the exceptional set. This is enough to say that the set where it applies this full Hausdorff dimension. So how are we able to do this? So we use dispersion. So this is another way to look at the distribution of some points mod form. And instead of asking to have the right number of points in a box, we just want to have 1 point in a box. Right, so it's the largest gap. So if you're just looking at in 1 dimension, as we are, it's the largest gap. And what's the point of looking at the largest gap? Well, so if we can bound the size of the largest gap, so say there are no gaps bigger than d over t, then for any delta, there'll be some nt beta, some point nt beta, which is close to delta. The distance has to be smaller than the largest gap, right? So as you can see, it's a very natural thing to use. It's more directly relevant than the discrepancy. So let's go back with the discrepancy. The discrepancy is, like we say, the right number of points in a box. So so in particular, there has to be at least 1 point is sort of what we're trying to say there. Whereas here we're just defining the dispersion to make sure that there's some point. It's just the size of the largest gap. And so, yeah, so because of this, we should expect it to give better results. But there's also a bit more going on. So it's actually not so much about the fact that we're looking for only 1 point. What's actually more relevant is the fact that we only have to consider 1 scale. Whereas with discrepancy theory, you're sort of considering many scales, and then morally it's saying something a bit different depending on what scale you're considering. You need sort of an accurate count at every scale. With dispersion, you only need it at 1 scale. So this sort of hints that dispersion should give better results. And we can also sort of guess how much better the results are by looking at random sequences. So I mentioned that the discrepancy is about n to the minus a half. Dispersion is about n to the minus 1. If you have uniform random variables, then with high probability the dispersion is about log n over n up to constants. And if you take those constants to 0, infinity, and infinity, then this probability will go to 1. So the dispersion is about 1 over n, or about log n over n, almost surely, compared to the discrepancy, which is something like n to the minus a half. So we should expect dispersion to be discrepancy, but also quite soundly, by about the amount that I claimed in the results. And we prove a dispersion estimate. So this is this is how we get the Lachenary approximation result, which then gives the multiplicative approximation result. We prove a dispersion estimate. So we take some Lachenary sequence of n1, n2, and so on, and we dilate the sequence by some beta, which is generic with respect to polynomial Fourier decaying measure. And then we look at the dispersion of the NT betas, and we bound it by log t to the 3 plus epsilon over t. So, I guess, yeah, so random would be something like log t over t. And here we have like a log square loss, but we're still quite close to the random heuristic. We get this dispersion estimate for almost all beta, and that gives yeah, and we conclude the previous results I found. So that still raises a question of how do you prove the dispersion estimate? How do you get a point in one of these boxes? On. So we use Fourier analysis. We count with some sort of smooth weight. We just want 1 point, but we'll get many points actually. We'll be able to count accurately at least when we put these smooth weights on. And then we look at a particular scale, which is log t to the 3 plus 2 epsilon. Epsilon's arbitrary, so the factor of 2 doesn't make a difference. And we look at this scale, d over t, and we find points there. So if we want to count how many there are, so we can apply Poisson summation, which enables us to say, well, the sum of these smooth things that over the integers will be the sum of the Fourier transforms, and we can sort of take out the zero frequency, gives a contribution of d. We L1 normalize the bump function and look at what's left is the non-zero frequencies, and we have this rapid Fourier decay, and we have this rapid Fourier decay, which means that we can ignore the sort of very high index frequencies. And how high is given by something called the uncertainty principle. So this says something like the Fourier transform is essentially supported on the dual. I guess we had to scale d over t, and the scale we will get is basically t over d with an extra epsilon of wiggle room, the reciprocal of the scale. So we consider, so we consider this in Fourier space, and because of the Fourier decay, we can cut off the very high index Fourier coefficients, and we get these finite sums. So we get some sort of Fourier coefficients which look like L times NT, and sums of these, or the number of L times NTs representing a certain index or certain number k. And so we understand the Fourier transform of this thing, and we can look at moments. We can look at moments we can look at moments of this by taking the absolute value and raising to the power of 2s. And taking integrating against mu. And so in Fourier space, what does this look like? This looks like sum of ak mu hat minus k, where ak is sort of the Fourier series for C0 raised to the 2s. And we would get pretty good results already if we took s to be fixed, but we pushed a bit harder by taking s to actually grow slowly with t. So the idea is to use a concentration argument. So we want the count to concentrate around its mean, and we get the concentration by bounding the moments, and we want to sort of accurately bound some fairly high moment. And we do that in Fourier space. So so when we expand this out, we also find that the contribution from large Fourier indices k is small, because we have this rapid Fourier decay, and we also have Lacunary sequences. And what we find is the main thing to bound is the contribution from small index frequencies. And when you expand out the expressions that we get something in front, and then times the number of these linear combinations of LJs and TJs that are at most k. So if you go back to the Fourier transform, there's some L that was at most capital L, and some T that was of size T, and we look at we look at the number of L times NTs. But then when we raise that to the power of 2s, we get these linear combinations of LJs and TJs. So then what we then get is we need to count how many solutions there are to this thing. This is some diophantine inequality, and it's some of the variables. So the LJs, so it's sort of bilinear. The LJs are free, and the NTJs, they run along a Lacunary sequence. So there's some sort of bilinear diophantine inequality where one set of variables is free and the other set of variables runs along a Lacunary sequence. Actually something like this had been done before, which I'll get to, but not at the level of generality that we needed. So what we do is we count solutions to a Lacunary diophantine inequality in quite some generality. So the y's have scale y, the z's have scale z, and you take you run along this Lacunary sequence AZs. And the bound that we get is so what we're sort of hoping for is diagonal behavior. So if you look at the previous inequality, I guess if we have Lj equals Ls plus j and Tj equals Ts plus j, that's a sort of diagonal solution. And maybe the diagonal solutions sort of dominate because the lacunarity of the sequence makes it hard to get these coincidences away from the diagonal. And the bound we get is sort of diagonal. So diagonal would be yz to the s over 2 here, but there's some logs. So there's logs to the s over 2, and there's an s factorial as well. So there's the other thing, because s we're taking to be large, it matters, the dependence on the number of variables s matters. So we have this result, this uniform in the number of variables. It allows for different ranges y and z. And also k is quite robust in terms of k. So as mentioned, this has been studied before. So Rudnick and Zaharescu had been studying some Poissonian statistics, point sequences modulo 1. And they'd studied this with k equals 0, so some Lacunary diophantine equation with y equals z, so the range is the same. The one set of variables is Lacunary, and s constant, so fixed number of variables. So we have a triple generalization of the result in this lemma. So I don't know if generalization is the right word, but yeah, we have to explicitly track the dependence on S, as well as generalizing to inequalities and to lopsided ranges. So, okay, so probably not a good idea to discuss the exact strategy in great detail, but discuss the general strategy. So this was gotten by Rudnick and Zaharescu. So so there's a sort of S factorial factor that comes from ordering, and otherwise you have so you have them already ordered, and you look at the indices that are close, where close is about log squared for safety, because when you take a Lacunary sequence, you're sort of exponentiating as you run along the sequence. And the point is that within a block, things can be sort of close, but in separate blocks, the contributions are vastly different. So we sort of look at the blocks in order, and we know that future blocks won't contribute very much. And within a block, we have this closeness, this proximity of the z variables, and bound those. And once we've bounded the proximity, once we've sort of fixed the z variables, then we've got some y variables, and we know that there's some constraint that comes from the knowledge that future blocks will contribute less. There's some sort of some sort of inequality. And then we're basically done, because we can use that, and we have a nice region. It's sort of a tubular region, and we're just solving in these free parameters. And there's a Lipschitz principle that says, well, you have a nice region, so the number of lattice points should be essentially bounded by the volume of that region. And the only catch here is that we need to explicitly track the dependence on the number of variables, the dimension of this space we're working in, and we do that. Yeah. Okay. So the strategy is a little bit more complicated than this, but this is the rough plan. Okay. That's all I have to say. So thanks very much.
Okay. Thank you, Sam. Well, I can do this, or we can do something virtual. Any questions? So I have a question. I mean, you had so many lemmas that I forgot what was actually the result. Can you show the result about Littlewood?
Oh, I had a few results.
That is proved. Yeah, I know that you have.
It's not all of them, but so one result was
extension
in
of
multiplicative approximation.
So you have the set of betas. Yeah, if you fix alpha, you have the set of betas with we're almost log. Okay.
So we win by essentially a log, and it's also inhomogeneous and also uniform in the shift delta. Yeah, we almost get Littlewood with the log. So it's I guess the limit of the method is probably log to the 1 plus epsilon. Would be possible in principle, although yeah, we did you know, we worked fairly hard, so we took a non-constant moment and all that. But yeah, if one used to sort of if one could establish sort of random behavior, then one would get and use dispersion, one would get log n over log n. Yeah.
And this is so you did it by applying your abstract results about Fourier decaying measures to Kaufman measures.
So yeah, we applied abstract results about Fourier decaying measures to Kaufman measures. That also got full dimension, and so these are sort of Lachenary approximation. Yeah, so we can state those results in terms of multiplicative approximation, but then to do that, to prove it, we used Lachenary approximation. So we approximated alpha well along a Lachenary sequence, and then we approximated beta.
Yeah. Okay. Yeah. So if you decide to abandon deltas and only look for delta equal to 0, it's not getting any easier.
That is easier, yes. So if you take
just homogeneous version,
delta equals 0, or even if you took delta fixed and didn't insist on uniformity on G being independent of delta, then it does become easier. You don't get much stronger results, but say there's work, I guess that if you take delta equals 0, then there's work of Pollington and Blarney from 2000, where they also used these Kaufman measures, and they did Lachenary approximation. It's also used for analysis, and then you could get 1 over log, so you could beat Littlewood by a log. and if you fix delta, so that is allow G to depend on delta, then you can also do that. So there was some work of Pollington, Bellani, Zafiropoulos, and Zorin as well. So yeah, I guess yeah, here we have a method that's also gives uniformity of the set in delta.
Okay, I see. All right. Any other questions? Comments? Anything?
Wait, so you're saying that with a fixed delta, you get this as 1 over log with no numerator expression.
Right.
I mean, is it silly to ask then what one can get if for almost every delta?
For almost every delta? Yeah. I mean, no, it's not silly. Yeah. So let's see.
So it's for fixed alpha and beta. What exactly? What is the question?
Well, so if I understand, so with the theorems on the screen right now, if instead delta is a fixed number,
so
then
you want a set of betas for which something happens for a full measure of deltas?
Yes, exactly.
So will it be any improvement of that? Maybe not. No. Probably it will not improve much, but it's just a conjecture.
Yeah, I can't immediately see any way to use that to improve on what you get for a fixed delta. We do have an argument to get results for a full dimensional set of pairs beta delta, such that beta is not only badly approximable but also delta inhomogeneously badly approximable. Which means that n times the distance from n beta minus delta to the nearest integer is bounded away from 0. And so that sort of says how does it work? So we have yeah, so we have some result that works for all delta, and then for almost all delta, there's a result by Jimmy Tseng. So this is called twisted approximation, as you know, for almost all delta. Yeah, beta is delta inhomogeneously badly approximable. So then you get a full dimensional set of fibers and a full dimensional set of betas, and you can piece them together using using a version of mass slicing theorem. So this is in my paper with Manas, and it's also in our paper.
Other comments or questions? Okay, if there are no questions, let's thank Sam again. It was a nice talk.
Thanks, Sam.
Thank you. And we'll meet next week for another talk.